Okay, class, welcome back to another fun installment of AP Calculus. Today we're going to be talking about the second fundamental theorem of calculus. Now this is going to be a little bit trickier than the first fundamental theorem of calculus, which, as you remember, was definitely like a load lifted off. So we were doing all this crazy stuff with finding the area of the curve. We had limits, we had sigma functions, we had rectangles out the wazoo. All of a sudden, out pops the first fundamental theorem of calculus. With definite integrals, our life gets easier, and we love the fundamental theorem of calculus all of a sudden. The second fundamental theorem of calculus is definitely going to be a little bit more challenging. It's definitely going to be a little bit more of a tenuous relationship if you had such a good one with the first fundamental theorem of calculus. So let's go ahead and jump right into it. Here we're talking about the second fundamental theorem of calculus. Really important. Now this one is much, much more powerful than the first, and actually it sort of springboards off of the first. But with this, if you fully understand what the second fundamental theorem of calculus is, A, fantastic, good on you, it's really hard to do, but B, it's really, really powerful. Now, before we get into that, let's go ahead and refresh ourselves. Here we're going to start off talking about definite integrals. Now, if you remember from the first fundamental theorem of calculus, we've got our integral from b to a f of x dx. And so here we've got a set interval, right? So we go from a to b. So we have two constants, or basically we just have a set interval. So we have f of x is a function, we've got two constants, all is good in the world. Now, I'm going to rewrite this. Okay, instead of x's, I'm going to use t's, and instead of constants in the integrand, or constants that is going to be our interval, I'm going to go ahead and use x as one of the constants. Okay, now once again, we use variables because sometimes we don't know what a number is, right? It varies, so then we use a variable. So in this case, I'm going to say f of x, capital F of x, is going to be equal to, so some function of x, and this one is also a capital F of x. Some function of x is going to be equal to, so here's our integral, and this time it's going to go from x to a. So we have a fixed starting point, a. We do not know what our fixed ending point is, x. Okay, so we've got f as a function of x, and then here we've got some function f of t dt. Now where did these comes from? Where did these t's come from? Now these t's, they're just a variable that we're using. Now it might be just a placeholder variable that we don't really need, a dummy variable, similar to like when we were using the u's and differentiating. All of a sudden these u's started popping out. Here we're just going to start using t's. T's are going to pop out. So here's an example. Okay, so say I've got a cosine function. See, I've got a cosine function. I'm just going to go ahead and map this out. And my cosine function goes from 0 to pi over 2. Okay, now a cosine function, not super exciting over that interval. Basically, like it sort of comes down and hits the x-axis and we're done. Now, what if I'm trying to figure out what the area under this curve is, but I don't know. I know I'm starting at 0, but I don't know where I'm ending. Okay? So say I wanted to start from 0 and go to 0. Well, I know that there's not going to be any area there, right? So say instead of starting from 0 and going to 0, I wanted to go to pi over 6, which is about a third of the way across here. So here I've got pi over 6. See, I want to know what the area under the curve was right here, just in between this interval right here. So I'm going to pull out my highlighter. I'm going to highlight this area. Okay, how would I calculate that? Well, now you guys know how to do that. You can set up that interval. Now, what if instead of pi over 6, I wanted pi over 4, or pi over 3, or pi over 2, or I just could keep going and going and going? So basically, the problem that I'm going to give you is, say f of x is going to be equal to the integral. So this is the area I'm trying to find from x. I don't know where I'm stopping to 0. And I'm going to call this the cosine, instead of x down here, I'm going to leave this as t, cosine of t dt. Okay, so here's my t's getting thrown in there. Once again, and I'm asked to evaluate what the area under the curve is when x is going to be equal to 0, pi over 6, pi over 4, pi over 3, pi over 2, dot, 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 dot. We'll stop there. Okay, so here I've got a lot of calculus. This would be like a lot of integrating if I wasn't using this other variable's t or this other variable x. Okay, so I could set it up as 5 different definite integrals, 1, 2, 3, 4, 5. Or I could just do one of them and see what happens with this variable x. Okay, so let's go ahead and do that. So if I start off with from x to 0, the cosine of t dot dt is going to be equal to, so now before I even think about this x, let me just solve this antiderivative. So cosine of t, okay, the antiderivative of that is just going to be the sine of t. Sine of t, and I'm going to go from x to 0. Now I'm looking at f of b minus f of a. F of b minus f of a, remember b's at the top. So f of b in this case, when I plug x into my sine t, I'm just going to get the sine of x. Minus, now my f of a is just going to be the sine of 0. Once again, x is a variable, 0 is a constant. I know I'm always starting from 0 in this case. Now the sine of 0 is just going to be 0. So all of a sudden, I've got this function, f of x is just going to be equal to the sine of x. So I've got this, I started with this really ugly calculus thing. It's talking about the area underneath the curve. I end up with the function is equal to the sine of x. And now all I need to do is solve for this function when x is going to be equal to 0, pi over 6, pi over 4, pi over 3, and pi over 2. Which is easy. I just plug it in there. I use my unit circle or use my calculator, whatever it takes to figure it out. And so basically, if you do that, you find, sure enough, that f of 0 is going to be equal to 0, right? So that's just from 0 to 0. That was one of our properties of definite integrals we learned yesterday. If your limits are going to be the same and the area is going to be 0. And f of pi over 6 is going to be equal to 1/2, right? So the sine of pi over 6 is 1/2. F of pi over 4 is equal to root 2 over 2. F of pi over 3 is going to be equal to root 3 over 2. And finally, f of pi over 2 is going to be equal to 1. So we can see as I start marching outward here, so pi over 6, pi over 4, pi over 3, about there, and then pi over 2. So from each one of these intervals, I can see my area is getting bigger. And you can plug these into a calculator. So 1/2, that's 0.5. This is 0.707, 0.866, and then 1. So sure enough, like my area is getting bigger and bigger and bigger as I march out towards pi over 2. Now where does this come into play as far as the second fundamental theorem of calculus? Now I'm just going to throw the second fundamental theorem of calculus at you guys and try to explain it as I go. It might seem really simple, it might seem really obvious at first, but once again, it gets really complex quickly and the applications are really, really numerous. So here we go. The second fundamental theorem of calculus. Here it is. F is continuous on an interval containing a and then x. So it's going from x to a, right? This is going to seem really sort of obvious and simple. So if I take the derivative of my antiderivative, then I get my original function. So basically here I've got the antiderivative. So I'm taking the integral from x to a of f of t, dt, right? So that's going to be my antiderivative of some function. If I take the derivative of that function, then I get my original function back. Not all that groundbreaking, right? So of course, if I take the derivative of my antiderivative, logic tells me sort of opposites. You know, one is pushing one way, one is pulling the other way. And so basically, like it just sort of cancels each other out. Now I'm going to start you guys off with a simple example, and we're going to go into a little bit more complicated example. So a simple example where to use this is if I just straight told you, okay, I want you to evaluate this function. d dx x0 square root of t squared plus 1 dt. Okay, so already knowing what we know about the fundamental theorem. So here I've got an integral from 0 to x, right? So I've got the antiderivative of this function. I'm taking the derivative of the antiderivative. So sure enough, you know, I've got this function and it's continuous from 0 to x, so that's fine. Basically, I can just rewrite this and say that this is going to be equal to the square root of x squared plus 1, right? So here I've got some function, square root of t squared plus 1. That's going to be my f of t. Going from x to a, in this case x to 0, dt, dt, dx, dx. Basically, I just rewrite my f of t as f of x, and I'm done. That's it. Second fundamental theorem of calculus. Not too bad, not too bad. Now, when I start throwing in things like the chain rule, this is where it gets tricky, complicated, and you guys are going to need some bragging rights to be able to fully understand this. Or when you fully understand it, you'll earn some bragging rights. So here's a much tougher example. And this is going to require you guys to dig back into what the chain rule of differentiation is. Okay. So first thing is I'm asking you, okay, so find the first derivative. Or find the derivative of this function. F of x is going to be equal to x cubed is one of my limits. Okay, so no longer are we talking about just x, but we're talking about x cubed. And we're going pi over 2 is our lower limit, or our lower interval, of the cosine of t dt. I know, mind blown, crazy. We're talking about Chinese language here, okay, foreign language. How in the world would we even start to think about solving this problem? Well, the first thing I'm gonna think about is substituting. And this is something that I want you guys to get into the habit of. Anytime you see something really, really crazy like this, start substituting. Okay, so here the big thing that I'm worried about is this x cubed. How am I ever going to deal with this x cubed? So I'm going to start substituting. So I'm going to use these dummy variables. Okay, and in the chain rule we used u. In this case, I'm going to say u is going to be equal to x cubed. Okay, so I'm just setting this. Set this. Just pull it out of wherever you want to, just set it. Okay? And so then I know that, okay, if I'm finding the derivative of this function, so what I'm looking for is f prime of x. Now I know that this is going to be equal to df dx, but because I've got this dummy variable, right, and it's going to be in terms of u, I need to use my chain rule. Now if you remember, the chain rule said basically I could take the derivative of the outer function, leaving the inner function the same, and then multiply it by the derivative of the inner function. Okay, a little bit crazy. Another way to write that with d's and df and du's and dx's and stuff like that is, if you remember, and this is probably way back in your notes, df over du times du over dx. And this is also going to look a little bit similar if you remember stuff from implicit differentiation, where we had a function with x's and y's, and we were trying to figure out how do I find, you know, you had to take the derivative and solve for y, you know, you'd end up with y primes on both sides, and you have to rearrange the equation and solve for y prime and divide by stuff, and you got some crazy stuff. You guys did great on that. Now here's sort of the same thing. So I've got df over dx, and I throw a couple du's in here. I can see I can sort of cross them out here, and this totally makes sense. Totally makes sense. So the du's cross out. So now, once again, I've got this dummy variable that I just sort of made up. Okay? And so now I just need to start working with this equation and plugging in stuff here and seeing what comes up. Okay? So here I've got, instead of df du, I'm basically just going to say d du of, and this is going to be f of x times du dx. Now the reason I'm going from here to here, this isn't a huge leap. Basically I'm just pulling this f out front and calling it f of x. The reason I'm going from here to here is to make it really obvious that I know what f of x is. It's this whole thing. It's what was given to me. So now I can just plug this in. So I can say ddu of, instead of f of x, I can plug this in right here. X cubed pi over 2 cosine of t dt. Now, if you're not entirely sure where I'm going with this, that's totally fine. Just bear with me. This is complex stuff. Complex math. Welcome to AP. So here we go. Now what I need to do is start substituting in, getting rid of these x's and plugging them into u's. Now this is totally fine because later I'm going to go ahead and do the opposite of this. Instead of x's and u's, or substituting x's for u's, I'm going to substitute u's for x's. Okay? So in this case, I say u is equal to x cubed. So I can say, all right, d du of, now all I'm going to do is just get rid of this x cubed. So instead of x cubed, now I've got from u to pi over 2. This is much nicer already. Cosine of t dt. Starting to freak out a little bit less because now I've got rid of that x cubed up there. And then I've got du dx over here. Now there's a couple things that I can do right now. One is I recognize, hey, this is u. And du dx, this is my little sidebar over here. Du dx is just equal to u prime. And u prime, I can figure that what that is really easily. You guys got this. It's just going to be 3x squared. So I take the derivative with respect to x, 3x squared. Now du dx, that's exactly what this is. So 3x squared I can just plug right in there. And sure enough, this thing right here, this is going back to my second fundamental theorem of calculus. So I've got this thing right here. This is exactly what we just wrote down. If I take the derivative of something, right? So let me do sort of a side by side. If I take the derivative of something, right? d dx of something right here in terms of t, and it's got an x in the interval. Sure enough, right here, if I do the same thing here, I can just rewrite the entire function in terms of u. So instead of rewriting this entire function, getting rid of the t's and plugging in x's, here I can get rid of the t's and plug in this u. So basically, I can just drop everything out. This whole thing right here just drops out to just the cosine of u. And then, of course, this du dx, as I mentioned before, just becomes 3x squared. Now, I'm not quite done yet, right? So I've still got this u I got to worry about. But sure enough, I know what u is equal to. U is exactly equal to x squared. So I've got the cosine of, or not x squared, x cubed. So I've got the cosine of x cubed times 3x squared. And sure enough, that's exactly what my answer is going to be. Exactly what my answer is going to be. We can verify this various ways, but I'm going to try to keep this video a little bit shorter, even though it's gotten much, much longer. We'll go over example problems like this in class tomorrow. I'll see you guys then.